So hypothesis testing. So we talked a little bit about hypothesis testing at the end of chapter 4, where we talked about confidence intervals, but now let's get into it a little deeper. All hypothesis tests have these two pieces at a minimum. You have some null hypothesis expected value, and so the technical name of a hypothesis test is usually a null hypothesis test, and there are some jokes about that. And then you have a sample observed value. So basically, you imagine what things might look like if devil's advocate position is correct, or if you're totally wrong about all of your stuff. And then you compare the actual data you found to that. You say, well, what would the data look like if I was just wrong about everything? Okay, now what did I find? How does that compare to me being wrong about everything? And then you make some sort of decision. You make that decision by comparing your null hypothesis value to your sample value that you observed from your data, from your study, from data collection. And you standardize that difference by comparing it in standard error units in the sampling distribution of the observed value itself. So if you're talking about a mean, if you have a sample mean and a null hypothesis mean, then you turn the difference between them into the number of standard errors that your observed mean is away from the null hypothesis mean, because you're comparing apples to apples. And if you're talking about a mean, then you have to look in a distribution of means to know how big that mean is, how far above or below that mean is from the, yeah, that was a terrible sentence, from the population mean. Then based on that, if there's a big enough difference, then you reject the null hypothesis. Then you say this whole thought experiment is not good. It's not what represents the world. I reject it, and therefore I provisionally accept my alternative hypothesis, which is the one I like. Or if the difference was not very big between these two things here, then you don't reject it. You fail to reject the null hypothesis, and you say, well, for now, the null hypothesis is where it's at. That's our best thing, our best theory. So then after you make that decision, you do a conclusion. The conclusion means you turn things back into the words, the original words, variables, and above all, answering the original research question that you were intending to answer in the first place. So you kind of bring it out of the theoretical mathematical realm and you drop it back in real life and say, okay, Mr. Director who hired me to do this, here's your answer. Here's the answer to your question. This is what I found out. So getting a little more technical, the procedure is to specify both hypotheses, the null hypothesis, which is the one you usually hope is not true, and then your hypothesis. Now, you're not going to find out which one is true. I just want to clarify this. We don't deal in truth in science in general, and we certainly don't deal in truth in statistics. There might be a truth, but we're not going to find it. What we will do is we will say, given the data, our best bet is to support the null hypothesis or to support the alternative hypothesis, even though we're not quite sure which one's true. We don't really say it like that, but that's kind of what it means. So we specify these hypotheses. We draw and label a graph. This is really important for me personally as an instructor, because for me personally as a person trying to understand statistics, this is how I do it. We find a critical value. So we find the number of standard errors away from the mean that you would need to get before you'd feel comfortable rejecting that null hypothesis. So it's kind of like a car salesman, you know, what'll it take to put you in this car today? That phrase, how annoying. But it's like you're saying, this is what it will take. This is the number of standard errors of difference there should be between my sample mean and the population mean that the null hypothesis says should be true, for me to conclude that I really have found something here, that my sample mean is different. My sample mean comes from a different population than that null hypothesis population. So we calculate the observed z-value, and that's our sample mean. We compare that to the critical z-value, which is sort of our benchmark, the value to beat. We compare the two together, and then based on the comparison, we make a decision about the null hypothesis. Notice that we don't ever directly make a decision about the alternative hypothesis. The decision about the null is we either reject it or we fail to reject it. Some people say retain it. And then based on that, we just kind of say, therefore, I either retain or reject my alternative hypothesis. Not the most logically rigorous procedure in the world, and it's been criticized for this a lot. Then we finally state our conclusion, which is going back to the original research question and answering it. and giving the information that we need to. The technical part is calculating the z observed. Finding the z critical is a little technical. You look it up in a table. Calculating z observed, sometimes the formulas start to look a little crazy, but at heart they're all exactly the same. An observed z-value for any kind of hypothesis test, or an observed z-like value, sometimes they're not z's, but they're similar to z's in many ways. That value is going to be the point estimate from your study, so like your sample mean, for instance, subtracting from that the null hypothesis value, and then dividing by the standard error. So your sample mean minus the mean of the null hypothesis distribution, and divided by the standard error of the mean, for instance. So when we calculate that, we have enough information to answer our question. And that's kind of more or less the end of the process. You calculate, you answer the question, you put your books away, go home. So it's good to get our ducks in a row before we start and see what kind of information that we have in front of us. We're going to need to know what the sample point estimate is. Now, most of the time it's going to be a mean for the next few weeks in this class. And we need to think what population value it estimates. Now, that can get a little deep trying to imagine which population our sample was taken from. And it seems so simple on paper, but in reality, it can be really pretty complex and almost philosophical to decide which population your sample was taken from. Of course, if you do extremely good sampling, it's much less philosophical and much more clear. What's the sampling distribution of the point estimate? We need to think what that distribution is, and above all, be clear that that's the distribution we're dealing with, the sampling distribution of the mean, for instance. We need to imagine what kind of individual values make up that distribution. Try to imagine them all because it's an infinite number, but try and imagine what's there. Remember that for the sampling distribution of means, it's a distribution of means, and so your sample mean is just one among many, many, many other means. It's like it went home to its home planet of means so that it can compare itself to all the other means and determine whether it's an awesome mean or not. It can't compare it to all these mortals here in raw score land. This metaphor is getting pretty crazy. So what is the mean of the distribution of means, of the sampling distribution? Now, this is an interesting question, and it has different answers depending on whether you're doing a confidence interval or a hypothesis test. For a confidence interval, it was the sample point estimate. You take your sample mean for a confidence interval for a mean, and you say, well, for now, we're going to assume, or just kind of a utilitarian assumption for a few minutes, we're going to assume that the population mean is actually the mean of my sample, which is crazy and silly, but it's useful for a few moments. But for hypothesis tests, we assume that the mean of the distribution of means is the expected value of the null hypothesis. So if the null hypothesis, by the way, expected value means sort of like the mean. So if the mean of the null hypothesis, if the null hypothesis mean that we're comparing our sample mean to is like 12, well then the mean of the sampling distribution of means is 12. Often when we're comparing two means, it's 0. But for one mean, we have to think a little more carefully. And then we need to think, so we can calculate z-scores, what is the standard deviation that we use in calculating that z-scores? Well, it needs to be the standard deviation of the sampling distribution, not the raw score distribution. And the standard deviation of a sampling distribution is called a standard error. So the standard error of the mean most of the time. So let's look at single mean hypothesis tests. Now, you can do a one-sample z-test or one-sample t-test, and the next little brief lecture will do the latter, but let's stick with z-scores because they're slightly easier. So this always works this way. You have some variable, and you collect some data on it, and you find some numbers, and you calculate a mean, and there you go. There's your sample mean. It's somewhere on that number line for that variable. And then you specify a null hypothesis value. And so the hypothesis test can be seen as answering this question. Is this value, this null hypothesis value, a plausible explanation for where this sample value came from? It's like you find this sample value and you say, where did you come from, little sample value? Where did you come from, little mean? Did you come from that big, nasty null hypothesis town over there? No wonder you've been so abused. Or did you come from Alternativeville? Oh, come in my house, you shoot. My metaphors are out of control today. I just need to stop. So this single mean hypothesis test, and if we use a z-score, we're going to call it a one-sample z-test, is where we take the mean of a single sample that we have calculated. We collected some data and we found a sample mean, and we compare that to a null hypothesis value, a null hypothesis expected value, the mean of some null hypothesized distribution. and we try and see if it's big enough that we can reject that null hypothesis concept completely in favor of something that we like more, our alternative hypothesis. So that's what this process is. Now that null hypothesis value, choosing it can be a bit picky, especially with a one sample test. Unfortunately, for a two sample test, you just say it's 0, which is not the best practice, but we're going to talk about that later. But for this, we need to think. Now that null hypothesis expected value might be some sort of a population value that's already known. It might be a value that's been theorized by somebody. It might be some sort of a value that is none of the above, but still functions as some sort of benchmark value to compare against. But it needs to be something that is meaningful in some way, that makes a meaningful comparison. So let's look at some examples of some of those. A known population value. Let's say you get a sample of some ACT verbal test scores from your school. You might compare that to the ACT verbal test national mean to see whether your sample has a different average score from the national mean. That might be something you could do. Now, none of these are the way to do a null hypothesis for these variables. It all depends on your research question, but they're examples. Let's say you're looking at the age of some CEOs of a few companies you found. Well, maybe you would want to compare those to the mean age of all Fortune 500 CEOs, for instance. So empirically known national population values, or not national, just population, which might be national. You could look at a theorized value. Now, this isn't empirical data that's been collected. This is somebody's theory. And if it's a theory that's worth taking seriously, then maybe it's a theory that's worth being a null hypothesis for somebody. So I made some crap up about somebody named Garcia in the physical sciences. Garcia's theory suggests that the population mean is 12.7 degrees. So maybe we do a study and we say, well, we think that the substrate will actually rise to a slightly higher temperature. So we'll compare it against Garcia's theory. Rush Limbaugh claims that illegal immigration is a net drain on the economy. That's a null hypothesis, or it can be. You can say, well, Limbaugh says it's a net drain, so we can collect some data and see if it fits that pattern of being a net drain. Now, Limbaugh probably didn't have data. Garcia might not have had data. They theorized. They came up with something. Another thing we can look at is just a benchmark value, kind of taken from our cultural consciousness, things that we all agree are sort of big, important milestone points in a certain variable. So here's some examples. A B average or a C average or something. That's kind of a benchmark value in education, even though it doesn't mean that there's actually some group out there that has a B average. But still, we think, are you a B average student? Is this a B average campus, etc.? So we could take a sample and compare it against this B average benchmark. So maybe a GPA of 3.0 could be our null hypothesis mean value. We could look at some people on a track team. And the 1 minute mile was a big benchmark in the history of running, well, the modern history of running. So we could say, does this track team, do they perform on average faster than a 1 minute mile? So those are some examples. Now here's some things that we want to get together. It's a list you saw before, but let's look at this more specifically for the case of a single sample mean, the same list you saw a few minutes ago. What is the sample point estimate? It's going to be the sample mean. What's the sampling distribution of that estimate? The sampling distribution of the mean. In other words, all possible sample means that might have been drawn from the same population our sample came from, with the same sample size our sample has, using the same sampling method. So kind of a mental leap, but easy to draw on a piece of paper. What is the mean of that sampling distribution of means? It's going to be the null hypothesis mean, the expected value of the null hypothesis. And as we saw on the previous slide, we choose that from outside the study. The researcher chooses that. And then what's the standard error or the standard deviation of the sampling distribution of the mean? You actually have two choices, and we're going to get into this a little bit. At first, we're going to use choice number A. You look at the population standard deviation divided by the square root of n. Or if you don't know the population standard deviation, as we talked about very briefly with confidence intervals, you can estimate it. But if you estimate it by using the sample standard deviation, by saying the sample standard deviation is a stand-in for the population standard deviation, which we don't happen to know, well, then you have to kind of hedge because of your uncertainty and make it bigger by dividing by the square root of n minus 1 instead of n. So anyway, you just use one of those two formulas, just to not get too complicated. For confidence intervals, this was the sample mean, remember this. But for hypothesis tests, it's the null hypothesis mean. So that's a difference between confidence intervals and the null hypothesis mean. So more conceptually, let's look at the setup that we're doing here. We start out with some variable, and we collect some data, so we find a sample mean. It's somewhere there. What do we do with that mean? How do we tell how big it is? How do we tell if it means something to us? Well, null hypothesis testing, the procedure says, we imagine, worst case scenario, or a plausible worst case scenario, right? We imagine a null hypothesis mean that we're going to compare against. And then we have to imagine the entire distribution of that null hypothesis. Then we have to imagine randomly sampling over and over and over again from that distribution to get millions and millions of sample means taken from samples of the same sample size, and the only way those things are different from each other is that it was random sampling. And random means a bunch of different things happen. So our mean is just one of many random samples. And so our mean could have been far away from the null hypothesis mean or close to it. So this is the world of the null hypothesis. We say, if the null hypothesis were true, that's what this diagram means, then where does our sample mean fit in the range of sample means that could have happened if the null hypothesis was true? Well, after doing all that sampling, we can put all those means together into a new distribution. And that new distribution is the sampling distribution of means. And the standard deviation of that new distribution is the standard error of the mean, which I made with a little two-headed arrow, which is kind of a weird way to draw it, but I guess I got it from an old teacher. I mean, a former teacher. Nobody's old, really. And then we look at our sample mean, we put it into that distribution of other means, that sampling distribution of means, and we see where it fits. And we ask ourselves, does it make sense that this sample mean came from this process of randomly sampling from the null hypothesis? Does it make sense that our sampling mean came from the null hypothesis, that our sample mean came from the null hypothesis? So we always want to get to this point, the sampling distribution of all possible means that's implied by the null hypothesis, very important. In other words, that's implied by assuming the null hypothesis is true, and our sample mean plotted on the same distribution. By the way, it won't always be to the right, it can be to the left, it could be almost in the middle, right? So the pattern never changes, it's always pretty much the same. So if we have like a sample size of 43 and it's something about temperature, we imagine the sample distribution or the raw score distribution, and then we imagine sampling millions of times, and the sampling distribution here, and let's say the standard deviation was 1.3, divided by the square root of 43, and that's the new standard deviation. So we imagine this sampling distribution of means, and that's the distribution in which we do our comparisons. And let's say your mean from n of 43 is somewhere, well, there you go, there's your mean. And maybe yours is a little higher. Now, that green area we do there, that's called P value. P stands for the probability of doing this random sampling from the raw score distribution over and over again, and calculating a whole bunch of means and making a distribution of means, and having one of those means be this one, or higher or lower. Anyway, this one or more distant from the mean, or more discrepant from the mean. So the area beyond your mean, going from the null hypothesis mean away from that mean, starting at your mean and going away, that area is called P, which stands for the probability of all that stuff I just said. So we calculate the p-value, which is a quick and dirty way to let us know how quick, actually it's a somewhat complex way, to let us know how far away our mean is from the null hypothesis mean. So let's say here's another possibility, and it's age. We calculate the standard error. Maybe your mean is 200, from an n of 249 is 92.3, which is lower than the population mean, and we calculate the p-value there. Let's say, here's another example. I don't even know how many I put in here. I had fun making them though. So here's 2 point something something or others. Oh, it's GPAs. I should try and remember that when I make this. So here's an example with GPA, and this is a more distant GPA, more discrepant. Now you can see that the sample distribution, or sorry, the sample size, in this case a huge one, and the standard error, they both make a difference in how easy it is to find what we call statistical significance. A small p-value, look how small that green area is, which means our mean was kind of far away from this population mean right there. So we've got all these possibilities. This is how it always ends up. This is a number of fish, apparently. I don't know. Oh, this is the best one. Okay, the p-value of your mom. I don't mean yours. I mean someone's in general. Maybe mine. So I'm just going to go back. I'm not going to go into this activity. Let's end right there. And I'm going to stop this screen share. I'm going to end this video. And if you have any questions, feel free to email me, etc., etc., etc.